and hi, my name is Noreen Aqilla Binti Kamaruzaman. My ID project is 123. My supervisor is Associate Professor Dr. Amri bin Sulaiman. My title for this final year project investigation of tool life and wear progression of Carbide tool in turning Nimonic C263 under multi-coolant condition. For the introduction, Nimonic C263 alloy is workpiece material to be mentioned. The characteristic of this material excellent temperature strength, such as hard hardening, tensile strength, thermal factory resistance to corrosion, thermal stability, oxidation that make this alloy can be employed in different fields. Next, to study the effect of tool life during machining Nimonic C263 alloy, there are two machining conditions, which is in the dry and in the flat machining condition. The problem statement, Nimonic C263 great demand in industry, very difficult during machining where the materials is low conductivity at the higher temperature, wood hardening tendency, and rough particle formation in its structure. The heat produced at the cutting zone can shorten the life of the tool. Then, during machining, material to heated due to the strength loss, chemical wear, and diffusion wear, thereby increase the rate of the tool. Objective from this study is to determine the significant factor on tool life of Carbide tool for both conditions, which is dry and flat, through the ANOVA analysis. And second, to investigate the tool life and wear progression during turning Nimonic C263 alloy under dry and flat. For the literature review, based on the past research study, I summarized that the research analysis, the cutting speed and the feed rate are the most significant factors that influence the tool life value. Then followed by that, the cutting speed and the feed rate from the researcher are still in the range for the new cutting parameter, which is the cutting parameter for the cutting speed is the 60 to 120 meter per minute. Is the flow chart for the overall experiment procedure. Material of Nimonic C263 as a workpiece with diameter 90 mm and 150 mm in the length of cylindrical for the turning process using CNC lathe ST20 with the high speed mentioning. By using the PVD1105 coated carbide tool as the cutting tool for machining dry and flat machining condition. Next, based on past research study, the best range of the cutting parameter value where the cutting speed which is 60 to 120 meter per minute, feed rate is 0.05 to 0.15 millimeter per revolution, and the depth of cut is 0.3 until 0.5 millimeter. From this cutting parameter, combination are being organized by using DOE, using RSM. Based on the RSM using Box-Baskin, the results show that the 17 experiments are being organized to run the sample of the experiment. The 13 operations are being evaluated when the flame wear VB is at 0.2 mm regarding to GIS B4011 1970. By using this method, we can determine the tool life and tool wear progression for the cutting tool. The result and discussion after experiment is done. In the dry machining, the results show that the maximum tool life value for the coated carbide insert tool of the experiment is 17.5 minutes at the cutting speed 60 and feed rate 0.05, depth of cut 0.5. Meanwhile, for minimum value is 1.21 minutes at the cutting speed 120 and feed rate 0.15, depth of cut is 0.4. On the other hand, for the flat machining condition, the maximum tool life value is 19.15 minutes at the cutting speed of 60 and feed rate 0.15, depth of cut 0.4. Meanwhile, the minimum is 1.91 minutes at the cutting speed 100. From the result, the value of tool life coated carbide tool under flat condition for machining Nimonic C263 is much more longer, 19.15 minutes when compared to the dry condition, which is 17.50 minutes. Then, the minimum value of tool life coated carbide for the flat are longer than the dry. This statement supported by Taya et al. 2022 state that the tool life significant increase by the application of the coolant as it maintained the thermal softening of the cutting tool insert. Low heat zone was observed around the tool workpiece interface, which improved the cutting tool life. Next, the effect of tool life also depends on the cutting speed, feed rate, and depth of cut. The first cutting parameter is cutting speed. The results show that the various cutting speed at the 60 and 120, the off-cut and feed rate is constant 0.3 and 0.1. The results show that the lower cutting speed gives the higher value of the two lives. Based on these two machining condition result, with the different cutting speed, the result observes that when the cutting speed at 60 have a higher to life value compared to the 120 for the Bush machining condition. This result is supported by Kumbra Wang Mare 2030, who observes that the increase of cutting speed will decrease the surface roughness and to life under cutting condition. Second cutting parameter is feed rate. When the value feed rate is various 0.05 and 0.15, the cutting speed and depth of cut is constant. The higher value of feed rate will affect the tool life value of the Carbide-2. When the feed rate is 0.05 compared to 0.15, the tool life value for the flooded machining condition is more longer than the dry machining. This statement is supported by the Talib 2010 that stated that maximum life occur with the minimum speed for all the feed rate value. Lastly, the results show that the effect changes for the value of depth of cut. When the depth of cut is 0.3 mm and 0.5 mm, when the cutting speed 120 and 0.1 feed rate is constant, the increase the value of depth of cut will affect the longest of value of the two lives. This statement is supported by the Sivarao Chakrada 2020, where the greatest two life at the lower value feed rate and the off-cut condition. From the ANOVA analysis of the two life Carbide insert PVD 1105, the result ANOVA table show that the F value of the cutting speed A 251.73 is greater than the F value of the feed rate B 30.65 and the F value that of cut C 0.074. On the other hand, for the flat machining condition, ANOVA table show that the same, which is A for the cutting speed is 468.05 is greater than the feed rate 3.83, followed by the depth of cut is 0.999. Then the value of probability more than F must be less than 0.05 to indicate that the model term are significant. For the both data, the dry and flat machining condition, the speed is more significant in determining the two life, then followed by the feed rate and depth of. To support the result from ANOVA analysis, here is a graph for one factor for each cutting parameter. They show that one factor plot of the two life of a coated Carbide-2 versus cutting speed, feed rate, and depth of cut for the dry and flat machining condition. The graph show that the cutting speed have the largest slope when to compare to the feed rate and depth of cut. The pattern of the slope for the cutting speed on the flat machining condition is larger than the dry condition. This statement is supported by the Anand and Harun 2015, who stated that the cutting speed had a steeper slope than the feed rate, thus indicate that the cutting speed had a greater impact to the tool life than the feed rate. The pattern and progression of the coated Carbide-2 PVD 1105 for the dry machining condition when the cutting parameter, which is at the 120 meter per minute cutting speed, 0.15 feed rate, and the off-cut 0.4 millimeter. With the cutting parameter, the tool only managed to travel 80 millimeter until the catastrophic fracture occurred. Meanwhile, for the 120 meter per minute cutting speed, feed rate 0.15 and the off-cut is 0.4, the tool managed to travel 320 millimeter until the catastrophic fracture. For the flat machining condition, for the cutting speed 120, feed rate 0.1, the off-cut 0.5 mm. The presence of the rapid wear is clearly the value of PB record was the 0.208 mm at the cutting distance 100 millimeter, and when the cutting speed at the 120, feed rate 0.1, the off-cut is 0.5, the tool only managed to travel 180 millimeter until the VB 0.201 mm catastrophic fracture occurred. From the result obtained, Cutting distance for the flat machining condition is 580 millimeter higher than the dry, which is a 320 millimeter. Based on the first objective, which is to determine the significant factor onto the two live carbide tool for the bush condition, dry and flat, through the ANOVA analysis, can conclude that based on ANOVA analysis, cutting speed is a more significant factor than the feed rate, then followed by the depth of cut in determining the tool life for the bush machining condition. The second objective is to investigate the tool life and the wear progression during turning Nimonic C2C3 alloy under dry and flat. It's found that the flame wear progression until VB flame wear achieved 0.2 mm. This wear progression can be classified into three stages, which is initial, middle, and final. High cutting speed will cause the short of tool life, while low cutting speed will cause a long tool life. High cutting speed during machining will increase the temperature, thus increase the flame wear progression and reduce the tool life. Machining conditions show the longer of tool life value for the maximum is 19.15 minutes and minimum is 1.96 minutes rather than the dry machining condition. Recommendation: first, dry and flat machining condition will be reduced to life of the cutting tool so that the cryogenic CO2 or minimum quantity lubrication (MQL) can be looked into feature study in terms of their tool life performance and cost effective. Second, cracker wear, chip formation, cutting force, and cutting temperature also can be studied and generate as a response. Lastly, high hardness of a cutting tool material should be applied in machining process to delay the wear progression